Hi, this is Shubhankar. I will be giving a short presentation on our work titled Reward-Based Autonomous Online Learning Framework for Resilient Cooperative Target Monitoring using a swarm of robots. Motivation: the advancement in robotics technologies, especially sensor and communication technologies, has made the use of robotic swarms quite attractive in many safety and success critical applications like disaster relief, search and rescue, firefighting, traffic monitoring, surveillance, etc. All such real-world applications involve target search and monitoring using the swarm of robots as one of the fundamental tasks. But due to adverse conditions or environmental uncertainty, the robots may undergo sensor failures, communication link drops, or target visual loss. Here, the idea of swarm intelligence can help us in tackling such issues. Swarm intelligence is characterized by decentralized local sensing and control, local communication, emergent self-organizing global behaviors. These characteristics are also seen in swarms that occur in the nature, for example, flock of birds, school of fish, and army of ants. SI is further characterized by three main advantages: scalability, robustness, and adaptability. And these three advantages are highly desirable to have in a robotic swarm in order to handle the uncertainty in high impact real world applications. And this is where distributed online learning can help us to induce artificial swarm intelligence in a swarm of robots. The problem of cooperative target monitoring that we have considered involves a swarm of robots communicating with each other with a limited communication range, where each robot is equipped with a proprioceptive sensor suit that includes an IMU or an INS responsible for the robot's position estimation, and an exteroceptive sensor suit including a radar or a lidar and a camera for the purpose of target detection, target position estimation, and monitoring. Each robot exhibits a limited field of view based on the properties of their exteroceptive sensors. Due to adverse conditions or environmental uncertainty, the robots may undergo permanent or intermittent sensor failures. That is, for some finite time duration, a robot may be fully functional, or the robot may face either a faulty exteroception or a faulty proprioception, or the robot may face both a faulty proprioception and exteroception simultaneously. Further, the robot swarm may undergo intermittent communication link drops and target visual loss. Given such an adverse or uncertain environment, the main focus of our work is to ensure accurate target position estimation by the robots in the swarm, which is one of the most crucial elements that contribute in successful cooperative target monitoring. In this regard, we propose the Autonomous Online Learning Framework, which is essentially a multi-agent information fusion framework that is fully decentralized. It involves an adaptive consensus-based information fusion process where the weights are tuned via a reward-driven online learning scheme. The AOL framework can be applied to such multi-agent problem settings where the agents have a shared environment, a common objective, a common information space, and each agent's performance is governed by a reward-like signal. Further, their performance or reward is influenced either directly or indirectly by how the agents fuse information from their communicating neighbors. In the cooperative target monitoring problem that we have considered, the robots are deployed in a region where they are tasked with searching and monitoring a target, and therefore they have a shared environment. They also have a common information space associated with target position estimate, and their performance is governed by target detection confidence that acts as a reward-like signal. Further, their performance or reward has an indirect dependence on the quality of their target position estimate. Under the framework of autonomous online learning, we present three AOL variants. These three AOL variants involve four phases, where their first three phases are the same, and the difference between them lies in their fourth phase, which is the learning phase. The first phase is the local estimation phase, in which the robot forms an intermediate estimate of the target position by combining its sensor estimate with its previous time social estimate of the target's position using local weights alpha. Then comes the communication phase, where the robot transmits and receives relevant information, including intermediate estimates and social weights from its neighboring robots. The third phase is the social estimation phase, where the robot combines its intermediate estimate with that of its neighbors using the shared information to form a social estimate of the target's position. The final phase is the learning phase, which is different for the three variants. The variant AOL-C uses a comparative loss function for updating its local weights alpha hat, whereas AOL-1P uses a novel perturbation greedy reward function for updating its local weights alpha hat. On the other hand, AOL-2P uses the perturbation greedy reward function for both its local weights and social weights alpha hat and W hat respectively. Further, all three variants use a multiplicative exponential weights update scheme, which is characterized by quick convergence given the learning rates are sufficiently large. Here is a systems diagram for each robot in the swarm, describing where the AOL block fits in the big picture. The exteroceptive sensors are responsible for target detection and producing the target detection confidence, along with a relative position estimate of the target. The proprioceptive sensors are responsible for giving the robot's position and yaw angle estimates. These estimates from both exteroceptive and proprioceptive sensors are then combined to form the combined sensor estimate of target's position, which is then used by the AOL block along with the robot's target detection confidence. The communication module broadcasts information provided by the AOL block and the exteroceptive sensors and receives the information relevant to the AOL block from neighboring robots. The AOL block's output is then provided to the control block, which then generates appropriate control commands to maneuver the robot. Theoretical analysis of the three AOL variants was carried out, and it was shown that under certain assumptions, both the local and social weights converge exponentially fast. In practice, these assumptions are satisfied if the neighborhood configuration, that is, the robots in the neighborhood, and the performance configuration, that is, each robot's detection confidence compared to that of its neighbors, remain fixed for some finite time duration but may change intermittently over time. We carried out a MATLAB simulation study in which 50% of the total number of robots chosen randomly undergo intermittent exteroception failures and permanent proprioception failures. The robots in the swarm also undergo intermittent communication link drops and target visual loss. Here is a sample simulation run for the variant AOL-1P for total number of robots equal to 5 and 30 respectively. Note that around 50% of the robots undergo sensor failures as denoted by the red colored crosses and dashed lines, and intermittent communication link drops along with target visual loss also occurs. Even in such an adverse situation, AOL-1P tries its best to ensure resilience in the robotic swarm in order to carry out the task of cooperative target monitoring. Further, note that crowding occurs when the number of robots is too large, as in the case with n equals 30, due to which the robots, especially the faulty ones, obstruct each other, affecting each other's monitoring performance. The MATLAB simulation study involved comparison of the three AOL variants with the no communication case and the baseline algorithms averaging consensus fusion and Kalman consensus fusion. The plots shown here are scatter plots that show the final cumulative detection and closeness scores of the swarm at the end of 60 seconds for 100 simulation runs. The results show that AOL-1P performs 182.2%, 329.7%, and 652% better than the baselines in terms of cumulative detection score, and 94.7%, 138.6%, and 150.4% better than the baselines in terms of cumulative closeness score for n equals 5, 10, and 30 respectively. In summary, Kalman consensus fusion, which is a covariance-based fusion algorithm, performs poorly when sensor failures do not lead to an increase in the estimation covariance. Averaging consensus fusion, on the other hand, gives equal weights to all the estimates in the weighted fusion and therefore performs poorly under adverse scenarios where a considerable number of robots undergo sensor failures. All the three AOL variants perform better than the baselines. In particular, the best AOL performing variant, AOL-1P, which uses perturbation greedy reward in the local learning layer and uses detection confidence as reward in the social learning layer, performs significantly better than AOL-2P and the baselines. Further, we validated the top performing AOL variants, AOL-1P and AOL-C, using a ROS-Gazebo simulation setup, where the target is considered to be the robot Copernicus and the robotic swarm consists of robots Voltas. All the robots in the swarm are equipped with a 2D LiDAR and an Intel RealSense camera, and then each robot detection confidence is provided by YOLO v5. This is the AOL-C simulation video where the Copernicus robot is the target. Initially, the voltas spread out and surround the stationary target while maintaining some monitoring distance from it. Once the target starts to move, the robots chase the target in order to carry out the cooperative target monitoring task. AOL-1P is also validated in a similar fashion. And here as well, initially the robots spread out and surround the stationary target while maintaining some monitoring distance. And when the target starts to move, the robots chase the target in order to carry out the cooperative target monitoring task. In conclusion, we have considered the problem of cooperative target monitoring using a swarm of robots with a limited field of view and communication range that undergo permanent or temporary sensor failures, intermittent communication link drops, and target visual loss. For this problem setting, we propose a fully decentralized and adaptive information fusion framework called the Autonomous Online Learning Framework. The AOL framework involves an adaptive consensus-based information fusion process, including local and social estimation phases, where the local and social weights for the fusion process are updated via a reward-based online learning scheme. Under the AOL framework, 3 AOL algorithms are proposed, namely AOL-C, AOL-1P, and AOL-2P, where the difference lies in their reward functions that are used to update their weights. It is theoretically shown that the weights of all the 3 AOL variants converge exponentially fast under reasonable assumptions. Among the 3 AOL variants, AOL-1P performs the best, doing 182.2% to 652% and 94.7% to 150.4% better than the baselines in terms of cumulative detection score and cumulative closeness score per robot as the total number of robots increase from 5 to 30. Moreover, the AOL algorithms involve analytical expressions, making them computationally inexpensive and easy to implement, and thus quite suitable for implementation in swarm robotics. The AOL framework is quite generalizable. It can be useful in such multi-agent problem settings where the agents have a shared environment, a common objective, a common information space, where each agent's performance is governed by a reward-like signal, and this reward or performance gets influenced by the quality of information the agent has and how the agent fuses information from its neighbors. Therefore, the AOL framework can be used in applications like trading bots collaborating to increase profits, recommendation bots collaborating to improve customer reviews, multiple bots collaborating to search and detect societal threats on the web. Further, with some minor modifications in the reward function design, the AOL algorithms can be extended to solve the problem of cooperative monitoring of multiple identical targets. For example, making appropriate changes in the reward function to give penalty overcrowding around a single target.